Okay, so we had just derived the Schrödinger equation from the path integral. Now I promised that I would show you how to go the other way. That is, from the Schrödinger equation to the path integral. Okay, and that's what I want to do now. And this is much more straightforward. It's a little fiddly, but it's straightforward. The other one is actually less fiddly and more intuitive, but this one is, of course, a bit more technical, but straightforward. All right, so what does Schrödinger equation tells us? It tells us that, if I have, well, xn tn, x1 t1, the Heisenberg picture is xn u tn minus t1 acting on x1, and then u, according to Schrödinger equation, is e to the power minus I by h bar, the Hamiltonian, tn minus t1. Okay. So as before, what we do is that we subdivide the time interval tn minus t1 into n minus 1 small pieces. Each of length delta t. Sorry, each of length delta t, where delta t is tn minus t1 divided by n minus 1. Okay, so then what we can do is that we can just insert the decomposition of identity n minus 2 times, and then we will get k xn tn x1 t1 is equal to dxn minus 1 dxn minus 2 ... dx2. So right, so if you have, like, if this is my time interval, okay, so this is t1 and this is tn, then this is where it starts. Okay, so how many do we have here? What is n here? 1, 2, 3, 4, 5, 6, 7. N is 7, but how many gaps do we have? 1, 2, 3, 4, 5, 6. Okay, so we have 6. Yeah, so okay, so this is going to be the integral times all the, we're going to break up these guys, and we're going to have k from xn tn to xn minus 1 tn minus 1, and we're going to integrate over xn minus 1 over here. And then we're going to multiply that with kxn minus 1 tn minus 1 xn minus 2 tn minus 2, and we're going to integrate over the xn minus 2. So on and so forth until k x2 t2 comma x1 t1, and thus we're going to integrate over x2. See that there is no integral over x1 or xn. Okay, those are the endpoints. Now we can take each of one of these. So the idea is to have n to be very large so that the time interval is very small. So if the time interval is very small, we can take one of these arbitrary, we can take an arbitrary propagator, xn, tn, xn minus 1, tn minus 1, and then that would be, in the Schrödinger picture, it's written as xn, the time evolution from tn minus 1 to tn. Correct? Okay. And then what we do is that, well, it's a very small time interval, so we can expand this to first order. So we can expand this to first order. So this is going to be xn, the identity operator, minus I by h bar. I'm expanding the exponential. H, and this thing is nothing but what we're calling delta t. Okay? So we're ignoring terms that are higher order in delta t. Now, in this term, see that this guy is going to collide with this guy. And therefore, we can use in that expression xn, the inner product of xn and xn minus 1 is going to be a delta function of xn minus xn minus 1. But in quantum mechanics, delta functions give you normalization for the momentum eigenstates, and therefore we can write this as an integral over, with the prefactor 1 over 2 pi h bar, d of p e to the power I p xn minus xn minus 1 divided by h bar. Okay, so this is something we know from previous semesters of quantum mechanics. Okay, this is the normalization condition of the momentum eigenstates. Okay, now we move to the second term, this guy. The second term itself has two terms. One is the kinetic term, one is the potential term. So the second term, we can write this as I delta t by h bar. And now we have the bra of xn, and then we have the momentum squared operator divided by 2m, xn minus 1. And then we have xn, the potential energy term, sandwich with x, bra of xn and the ket of xn minus 1. Are you guys with me so far?
Yes, sir.
Okay, if anyone wants to stop, ask questions, I'm more than happy to do that, answer that. All right, so let's carry on. So we have already calculated the first term. The first term is this thing. The second term has two terms, the kinetic term and the potential term. And now we are going to massage the kinetic term. Our aim is to put all the terms in this kind of form, okay? So what we do is that we have x of n p hat squared by 2n, x of n minus 1. Then what we do is that we insert total identity. We insert identity here and decompose identity in terms of momentum eigenstates. We can call them whatever we like. Let's just call them, say, Pn. So let's call this Pn. Of course, that means that I have to have an integral here. Integral over dPn. And then I'm going to have p squared by 2m. So what I want to do is that I'm going to get rid of all the operators by applying them on some eigenbases. So here I can insert another eigenbasis. Let's call that Pn minus 1. Pn minus 1. So we have to have another integral over 2p dpn minus 1. And then there's xn minus 1. Now this thing acting on this will give me the eigenvalue squared. So in the next line, we can write this as dpn minus 1. And then we can write as pn squared. Now this is just a number. This is no longer an operator. And then we have xn pn. And then we have inner product of pn and pn minus 1, which is going to give us a delta function, of course. And then we have pn minus 1 of x of n minus 1. So, and then we can use this delta function and do one of the integrals. And if I do one of the integrals, I have left over, say, d of p of n. So we have p squared n by 2m. And then we have xn pn. And now this p just becomes pn times x of n minus 1. And then what we do is that these are momentum eigenstates, because this is a momentum eigenstate, and this is a position eigenstate. So this is the wave function of a momentum eigenstate. This is the complex conjugate of the wave function of a momentum eigenstate, right? So if I remind you, xp, this is a momentum eigenstate. Taking the inner product with the bra of x means that we are working out psi of p of x, right? And that is given by 1 over square root of 2 pi h bar e to the power minus I over h bar xn pn, sorry, xp. xp, okay? So if I do this, I apply it here, then I get that my inner product between xn, the operator p squared by 2m, x of n minus 1 is the integral over d of p, or I can call it pn. It doesn't matter. Let's call it pn. Then there's going to be pn squared by 2m e to the power I p xn minus xn minus 1. Okay? So this takes care of the second term in the Hamiltonian, this term. Now we come to the last term. And the last term is going to be xn v of x hat x of n minus 1. It's kind of easy to show that. Okay, let me just show it anyway. We can write this as xn v of, say, x plus x by 2 x of n minus 1. And then, we can just write this as, when these guys hit the polynomial, these things will change by this thing. And we can choose this thing to act on this and this thing to act on this, so that we take an average. So we get v of x of n plus x of n minus 1 divided by 2 times xn, the bracket of xn and x of n minus 1. Right? And this, of course, is a delta function, but the delta function can be expressed as an integral over the momentum eigenstates. So, and we can rewrite that IP xn, you can write it as n if you want, xn minus xn minus 1 v of the average of x. Okay, so all of this is now, so we have converted all those terms into C numbers. They are no longer operators. Operators are also called Q numbers. So C numbers is physicists use it to say classical numbers, things which are not quantum mechanical. And operators, sometimes physicists call Q numbers, okay? Because they are quantum numbers. Okay? It's a kind of a weird terminology. So K of x of n, t of n, x of n minus 1, t of n minus 1 is going to be, all these terms have 1 over 2 pi h bar and an integral over p. You can call it pn if you like. And then inside we have 1 minus I delta t over h bar. Then we have the term from the kinetic term and the potential term. And plus dot dot dot. And this is e to the I p over h xn minus xn minus 1. Okay? So we have converted one of the small operators, small propagators, into this very nice expression. Okay? So let me just use the index n here. N here. So now see that Pn squared over 2m is xn minus 1 squared divided by 2m delta t squared, right? So if I use this, I can rewrite this thing in the following way. K is going to be 1 over 2 pi h bar integral over, say, 2 pn. And now I'm going to exponentiate it because now this is just a small thing. So, up to second order, this is equal to the exponential. So I'm going to write this as e to the power minus I by h bar delta t times the Hamiltonian minus p times xn minus xn minus 1 by delta t. Okay, so what am I doing here? So over here, if you see, this is the Hamiltonian, right? Do you agree? This is the kinetic term, this is the potential term. And then we have, and then we have this guy, right? So this guy, if I put it over here within the bracket, I have to divide it by delta t because there was no delta t here, but there's a delta t here. But I'm putting in a bracket, I'm multiplying by delta t. So this becomes the Hamiltonian, and this is minus p, and this is the difference in the position divided by t. So this is, what is this? This is the velocity. Okay, this is x dot, the discrete version of the velocity. Okay, so now if I take the n equals to infinite limit, then I get the total propagator, which is k xn tn x1 t1. The limit goes from n goes to infinity, and then we have the integrals over the positions x minus 1, x minus 2 dot 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 dx2. But now for each of these propagators, we also get an integral over p, dp1 by 2 pi h bar dot dot dot. We get dp. How many do we get? I think we get dp. So we get from dpn down to dp2. Okay, so these are it's quite remarkable and quite important that we keep track of these numbers. Okay, and I'm going to come back to this in a moment. And in the limit, we have the exponential of I by h bar, And each of these little intervals, contribute this. So they're going to be a sum over delta t. So this is going to become an integral from t1 to tn. And inside the integral, I'm going to have the Hamiltonian minus px dot d of t. Okay. Those of you who are paying attention can recognize this as the Lagrangian. Okay, so let's see that this is this works out. So for example, if I take the simplest example where t one is here and t n is here, so tn is say t3, so I just divide it by 2, so this is t2. Then what am I going to do? I'm going to have one propagator here, and I'm going to have one propagator here. So we are going to have, if we have, say, so if n is 3, then we are going to have an integral over dp3 and then an integral over dp2, right? So this kind of thing works out. So then, so this is the expression for the path integral in phase space. This is not the expression that Feynman derived, but this is an important expression. The path integral can be expressed both in coordinate space or configuration space, as well as momentum space. So this is the integral over all the path in the position space, the integral over all the momentum, and divided by 2 pi h bar for each of these factors, and e to the power minus I by h bar, the integral from t1 to tn of the Hamiltonian minus px dot d of t. Okay, so this is the expression of the path integral in phase space.